Okay, so far we studied the magnetic force acting on charged particles that are free to move. So in such cases, they perform the circular motion due to the magnetic force, right? But in order for the current to flow, you will typically need wires. And if these charged particles are flowing in the wire, they are not really free to move. And as a result, the force acting on them will act directly to the wires. Okay, so take a look at the figure on the right side. Now we have a wire going up and down, and in the middle part there is a magnetic field coming out of the screen. Okay, and in the beginning there is no current, so therefore there will be no magnetic force. Okay, but then now in the second figure, now suppose the current is going up, and for simplicity let's assume that the positive charges are flowing, then the direction of this positive charges motion or velocity vector will be also going up. So therefore, by taking this cross product between the velocity vector and the magnetic field vector, you can easily find that the magnetic force will be acting to the right. So this force acting on these charged particles in this area will make the wire bend. So it's just like the force is acting directly on the wire. Okay, and then now suppose you change the direction of the current, so it's going down. Again, the direction of the velocity vector of this charged particles will be going down. So again, by taking a cross product between V and B, you will easily find the direction of the magnetic force will be going to left. Okay. So this is the qualitative description, but you have seen the direction of the magnetic force depending on the direction of the current, right? Okay, and then now we will discuss it quantitatively and try to find the size of this magnetic force. Okay, for simplicity of the description, we will assume that the wire is straight with the length L. Okay. And then here we have the magnetic field, uniform magnetic field coming out again, and this current is flowing up. Okay, and in this particular figure, the velocity of the particle is actually going down, which is opposite to the direction of the current. So what does it suggest? It actually, in this case, we are assuming that it is a negatively charged particle, which means electrons. Okay, so here we assume it's an electron. And then if you take the cross product between the velocity vector and then the magnetic field vector, you will get the vector going to the left. But because electrons are negatively charged, the force will be along opposite direction. So a force will be going to the right. Okay, so the direction of the force is correct. Okay, and then what we want to know is the size of the magnetic force. So let's think about it this way. So how long does it take for these charged particles to move across the distance L? Okay, so we assumed that this velocity is Vd, which is our drift velocity. Then the time taken for this travel will of course be length divided by the velocity, which is L divided by Vt. Okay, and then during this time period, if you have the current flowing by I, then how much charge has moved from one end to the other? Okay, so we know that current is actually defined as a time derivative of the charge. So if the current is uniform, then we can simply say the current is equal to charge divided by the time. So therefore, you can rewrite it so that Q will be current multiplied by the time, and insert this time that you have just calculated. Okay, and then now we already learned that the magnetic force is Q multiplied by Vd multiplied by B, or as long as these two vectors V and B are perpendicular to each other, which is the case here. Now we can directly write it using scalar notation, and then insert this Q that you have calculated, and then this is what you get. Here, take a notice that this velocity Vd disappeared, and which is very nice because we do not really know the velocity of the charged particles, and the only thing we know is the size of current in this case. So therefore, we finally found the magnetic force in terms of the size of the current, and then the length of this wire, and also the strength of the magnetic field. Okay, this is good. And this simple picture is the case when the magnetic field vector and the current vector are perpendicular. I'm sorry, current is not a vector. Okay, it was a mistake. Okay, again, this simple description was the case when the magnetic field vector is perpendicular to the direction of the wire. Okay, but then in some cases, the direction of the wire may not be perpendicular to the magnetic field. An example is shown here. So here, there's a magnetic field going to the right, but this current or the wire is at an angle phi. Okay, and again, current is not a vector, so you cannot use the current vector. So instead, you need a different type of vector. So we will represent this length as a vector, the length which is following the wire, and let's call this L vector. Okay, this L vector represents the length and direction of this wire. Okay, and it's making an angle phi with the magnetic field vector. Okay, so in this case, what will happen? How would it change? So you know that this direction of the wire is the direction of the charge's motion. And we already learned that when this velocity or the motion is parallel to the magnetic field, there will be no force, right? So therefore, what we need is the velocity component perpendicular to the magnetic field. And in that case, what you need is only the sine component. Okay, with this angle, you take the L multiplied by sine phi. Okay, which is effectively the velocity vector multiplied by the sine phi. Okay, so therefore this is what you get. So now comparing this with the above equation, instead of this simple VD, we will insert VD sine phi, and then finally what you will get is ILB sine phi. Okay, and then among the symbols shown here, maybe you can find the vectors. Okay, B is in fact a vector, and I told you that current is not a vector. It cannot be a vector, but we have chosen this L to be the vector, right? And then the sine phi is, of course, the angle between these two values. So therefore, we can simply rewrite it using the cross product between this L vector and B vector. Okay, so this vector representation of this magnetic force is actually looking similar to what we have learned before, and in fact it is the same thing. So if you have a charge, moving charge, then magnetic force was calculated this way. But now instead of moving charge, if you have a flow current, then now you can use this equation to find the magnetic field, magnetic force. Okay, and then the next question: what if the wire is not straight? Then what do you have to do? Well, if the wire is not straight, then in each section you will have a different L vector, right? Here the L vector will be going this way. Here the L vector will be going that way, and or here the L vector is going this way. But throughout the wire, current is the same, right? So therefore, that is why the current cannot be the vector. But then anyway, in this case, each piece will get some magnetic force. So suppose now in this particular position, then you are considering a small piece of this length, which is we call dl vector. And then and if it is subject to the magnetic field B and it is making an angle phi, then what you have to do is simply make a cross product between these two things. And then finally what you will get is not the total force, but a small piece of magnetic force acting only on this part. So if you want to calculate the total magnetic field, then what do you have to do? Of course, you have to integrate this from the area from the point to the other point over which you want to get the full value. Okay. Now let's try a very simple exercise about magnetic force acting on current carrying wires. Okay, here we have in the figure two conducting rails running along the y-axis, and they are not moving. Okay, and there is a straight conducting bar which is placed on top of this rail, and it can move. It can move left or right. And it is also connected to the string and also to the mass M. So by the gravitational force, it may be pulled to the right. Okay, and these two rails are connected to a battery. Okay, so battery is here, and then according to the direction of this positive terminal, the current must be flowing like this, right? Okay, and it's making a loop. Okay, and there is a magnetic field acting perpendicular, but we do not yet know the direction. It can be up or down, but we just know it's a perpendicular. Okay, and then this is the question we are going to ask. The first question: what is the direction of the magnetic field to generate a force along the minus y direction on the straight conductor? Okay, so here minus y direction means going to the left like this. Okay, and then okay, so what do we need? So try to remember, we have learned that magnetic force acting on current carrying wire is I multiplied by L vector cross B vector, and L vector is the length of this the wire or the conducting bar or anywhere the current is flowing. So in this case, we can see that this direction, this is the vector L. Okay, vector L is now going toward minus x direction, right? And then we want to find the magnetic force to be the minus y direction. Okay, and then according to the right hand rule and then the right hand convention of this xyz coordinate, if you make a cross product between x and z, then you will get minus y. Why? According to the circular rule, z cross x will be plus y. So therefore, x cross z will be minus y, right? So then minus y is what we need eventually. And then we have this L vector going to minus x, right? If this is minus, then in order to get the same sign, we need the minus g, right? So as a result, what we find is that now magnetic field has to be along minus g, which means that it has to be going down. So this is the correct one, and this is the wrong one. Okay, now the magnetic field has to go down. And then the next question is then, okay, now the magnetic field will pull this bar to the left, and then apparently this gravitational force will pull it to the right. And then we want a situation so that this conductor will be not moving. So the question is, what is the M, mass of the suspended mass, that allows the conductor to be at rest? So in this situation, of course, naturally, we have to find the balance of the force. So therefore, the magnetic force, which is ILB, should be equal to the mass mg. So you can simplify that the mass m must be ILB divided by g. Okay.